Alright, so our problem for today states that three tanks with cross-sectional areas of 0.5, 1, and 2 meters squared are interconnected at their bottoms with an initial fluid height level of 0.5, 1, and 2 meters respectively. The magnitude of the flow between the tanks is proportional to the square root of the difference in the fluid heights between the pairs of tanks. The proportionality constant between the two tanks is between tanks 1 and 2 and 2 and 3 are 0.1 respectively. Tank 3 drains to the surrounding height of 0 with the same proportionality constant. And then using the simplest form of control for fluid level in the third tank, which is proportional control, the flow into the second tank is set equal to a proportionality constant Kc equals 0.1 multiplied by the difference between the fluid level set point for the third tank, which is 4 meters, and its actual fluid level. So part 1 says we need to derive the differential equations to solve the fluid levels in the three tanks. So first thing we're going to want to do is draw out this situation so we can see and get an idea of what we're looking at. So we have three tanks. So here's our first tank. Here's our second tank. And here is our third tank. So they're connected to the bottoms. So they can just flow from here to here, and here to here, and that one flows out. And then we have a flow coming into the second tank here. And then, so all of these tanks have a different cross-sectional area, so you can label that. So this is, we'll call this A1 for the cross-sectional area of tank 1. A2, and A3. Okay, so then all of these tanks have some liquid in them to begin with. So tank 3 has like 0.5 meters of liquid, tank 2 has like 1 meter of liquid, tank 3 has 2 meters of liquid. So, and this is just our initial situation. These can change because we have liquid coming in and liquid going out over here. So then each of these tanks, we're going to need to find the heights of these liquids at any given time. So we better label those. So that's the height of tank 1, height of tank 2, and height of tank 3. Okay, and then let's label these flows. This is the flow coming in. This is the flow coming out. This is the flow from tanks 1 to tank 2. And this is the flow from tank 2 to tank 3. And then, so we're given what tank, the flow in is. So that's going to be Qn is equal to, so the flow into the second tank is set equal to a proportionality constant, Kc. So Kc multiplied by difference between the fluid level set point for the third tank. So you can call that HSP for height set point of the third tank. And its actual fluid level, so its actual fluid level is just H3. All right. So for the next, we're going to want to find, so we know what Qn is, we're going to want to find Q12, Q23, and Q out. So let's start with Q12. So Q12, it said was going to be proportionality constant. Okay, so we're going to use alphas for the proportionality constant, so we'll call this alpha 1, 2, this alpha 2, 3, that alpha 3. So that's just the proportionality constant between tanks 1 and 2, 2 and 3, and then 3 and the external system. So like not part of our system, it just goes out. But there is still a proportionality constant between this tank and the surrounding environment. So we're going to have Q12 is equal to this proportionality constant, 1, 2, times the difference in the tanks to the 1/2 power. So that's H1 minus H2 to 1/2 power. So this is what it's essentially going to be. But if we think about it, H1 minus H2 could be positive or negative depending on what these heights actually are. H1 is bigger than H2, then this is obviously going to be positive, and the square root will work out just fine. However, if H2 is greater than H1, so that the height of this liquid in here is greater than the height of that liquid there, then we're going to get a negative value in here, which will result in an error. So instead of just parentheses, we're going to want this to be an absolute value. And then, but we still need to account for the fact that sometimes, if the height in this tank is greater than the height in this tank, the flow is going to be going that way. However, if the height in this tank is bigger, it's going to be going that way. So we need a system for which direction is positive, which direction is negative. So the way I've drawn my arrows here, I'm just going to say that's the positive direction, so I'll write that up here. So this is the positive Q direction. So that is just the direction of our positive flow is that way. If it's flowing this way, it's going to be negative. And to account for this in here, we're just going to take the sign of this quantity here. I'm going to need more room to write that. So we're going to multiply this by the sign. Still going to need more room to write that. So we multiply this by the sign of H2 minus H1. So basically that says if H1 is greater than H2, then it's just going to multiply everything by a positive 1. If H2 is greater than H1, it's going to multiply everything by a negative 1, and so we'd get a negative flow, meaning that the flow would go that way if the height of tank 2 is greater than the height of tank 1, which is what we would expect in this situation. So then the flow for Q between tanks 2 and 3 is going to be very similar. So the flow from tanks 2 to 3 is going to be the sine of H2 minus H3, because now we're just dealing with tank 2 and tank 3 instead of 1 and 2. We're going to use the proportionality constant between those two tanks. And again, the absolute value of height 2 minus the height, the third height, to the 1/2 power. Alright. So those two, very similar, just with between the two different tanks. And then we've got Q out, which is again similar, slightly different though. So we're going to have Q out be equal to, so this one we're just dealing with one tank and the surrounding environment. So we don't need to worry about that. We're just looking at this one tank. So the sign's always going to be positive because the height here is always going to be, greater than everything else. So because we're not dealing with that, so we're just going to have, so we don't need the sign here at all because we're not subtracting heights. We're just using height 3. So we will need the proportionality constant. And so again, we won't need the absolute value because we're not subtracting anything. So then just times the height of 3 to the 1/2 power. So it's similar, but we're only dealing with one tank. Okay, so the next thing we're going to want to do is we're going to want to find an equation for, or set of equations for, the heights in these tanks. And these heights are going to be changing with time. And more importantly than that, the volumes of liquid in these tanks are going to be changing with time. And then the volume is going to be the area times the height. So, change in volume is going to be equal to a change in area times height. But the area is going to stay constant because it's going to be inside the same container and it has a constant cross-sectional area throughout. So we can pull that outside and we'll have the change in the volume is equal to area times the change in height. So that's how we're going to write change in volume for these problems. And then, so we can come over here, and we're going to want to write, an expression for the change in volume with relation to time for each of these three tanks. So we'll start with this first tank. So the change, so the area of tank 1 times the change in height of tank 1 over the change in time. So the change in volume with respect to time is going to be equal to, okay, so this is where we're going to get to our mass balance part of this problem. So conservation of matter and everything says that everything that goes in has to come out or get accumulated within the system. And so since we're looking for what is accumulated in the system, we're going to have, so the change of this is going to be the stuff that comes in minus the stuff that comes out will be equal to whatever is left inside. So nothing is coming into tank 1, so we just have what's going out, and Q12 is going out. And it's going out, so we'll have a negative for the flow out. Okay, and now let's move on to tank 2. So we're going to have cross-sectional area of tank 2 times the change in height of tank 2 over the change in time. So that quantity there is the change in volume in tank 2 with respect to time. Okay, so now we have Q12 going in. So that's going to be a positive. We have Q in going in. So plus Q in. And then we have Q23 coming out. So minus Q2. Alright, so now we just have to deal with tank 3. So we'll have the area of tank 3 times the change in height of tank 3 over the change in time is equal to, alright, so we've got Q23 going in, and then we've got Q out going out. Alright, and so now we have our equations that we're going to use to solve this problem. We're going to want to rearrange these ones a little bit because we're not looking for a change in volume, or we're not going to be solving for volume, we're going to be solving for height. So we can divide out these areas for each equation, and then I'll just write those down here. So for this top one, we'll divide out the area one, we'll get the change in the height 1, change in time. Actually, I might not have room to write these all here. This one I have room up here, so I'm going to do, we're actually going to do it up here. So we're going to have the change in the height 1 over the change in time is equal to negative Q12 over area 1. So I just rearranged that by dividing out the area. So now we have a relationship for the change in height with the change in time. Similar thing over here. But I don't think that one's going to fit right here, so I'm going to write this one down here. So we're going to have the change in height of tank 2 times the change in time is equal to Q12 plus Qn minus Q23 over cross-sectional area of tank 2. And then same deal for this one. So we'll have the change in height of tank 3 over the change in time equal to Q23 minus Q out over cross-sectional area of tank 3. So these are the equations that we are going to be using to solve for the height. Alright, so the part 2 of our problem says we want to simulate the dynamics of this controlled 3-tank system by solving the differential equations that we came up with in part 1 using scipy.integrate.solve IBP. So that will be using Python code, and is specifically this command in Python code. So we're going to open up a new workbook, and we want to first import our libraries. So we're going to want to import NumPy. We're going to want to import this scipy.integrate. And then we're going to want to plot our results. So alright. So next we can start with inputting what we know. So first thing it gives us is the cross-sectional areas of all 3 tanks are 0.5, 1, and 2. So call that A1, A2, and A3 is equal to 0.5, 1, and 2. And then it gives us that the initial heights of these tanks are 0.5, 1, and 2. So we use H naught for the initial heights. So H naught 1, 2, and 3 are going to be equal to 0.5, 1, and 2. And then we'll have the proportionality constants are 0.1. So we'll use an A for the alpha, so A1, or we had A12, A23, and A3, I believe. And here I just have a screenshot of the equations we derived earlier, so we can reference them, see if we had A12, or alpha 12, alpha 23, and alpha 3. Okay, and those were equal to 0.1. All right, and then we're giving that Kc is equal to 0.1. So and then that's the fluid level set point for the 3rd tank is 4 meters. So we called that HSP3. So HSP3, so that set point for the 3rd tank is 4 meters. Okay, so that's what we know going in. So now we're going to want to define the function that we're going to use solve IBP to solve for. So I'm going to define, and we're going to call this RHS for right hand side, because we're going to be solving, or this is going to return the right hand sides of these 3 equations. So the change in height with respect to time. And then we're going to want to put our inputs. So for solve IBP, you need to put your independent variable and then your dependent variable. So as I said, we're going to have changes in height with respect to time. So time is going to be our independent variable and height is going to be our dependent variable. So we'll have time, and then we'll have a vector of our heights. So then we can say that h1, h2, and h3 are equal to the vector. So we'll input them as a vector, and then it will split the vector into the height of tank 1, tank 2, and tank 3. So next, we're going to want to return these equations. So we can type that in. So we're going to want to return, and it'll be in an array. So negative q12 over a1. So the flow of tank 1 to 2 divided by the cross-sectional area 1. And then, so for tank 2, that was down here. So we'll have q12 plus qn minus q23 over a2. So flow from tank 1 to 2 plus the flow into tank 2 minus the flow from tanks 2 to 3 divided by the cross-sectional area of tank 2. And then we'll want it to return the third height, which is going to be q23 minus flow out of q23, flow out of tank 3 over the cross-sectional area of tank 3. So flow from tanks 2 to 3 minus the flow out of tank 3 divided by the cross-sectional area of tank 3. Okay, but it obviously doesn't know what Q12, Qin, Q23, and Qout are. That's why it's underlining them in yellow right now, so we're going to need to define those. So we need Q12, we'll need Q23, we'll need Qn, we'll need Qout. Okay. So let's start with Q12. So we come up with these equations for them. So that is going to, Q12 is going to be the sine of h1 minus h2. So the height of tank 1 minus the height of tank 2. So we can do np dot sine for that. And then height 1 minus height of tank 2. And then times alpha 1, 2, so proportionality constant between tanks 1 and 2. So alpha 1, 2 times the absolute value of the height 1 minus height 2 to the 1/2 power. So use np dot absolute, or abs, for the absolute value of height 1 minus height 2 to the 1/2 power. Or we'll put 3.5. Okay. So then for Q23, it's going to be very similar. So the equation is basically the same, except we have height 2 and 3 instead of 1 and 2. So we'll have np dot sine of the height of tank 2 minus the height of tank 3 times the proportionality constant between tanks 2 and 3 times the absolute value of the height of tank 2 minus the height of tank 3 to the 1/2 power. Alright, so now for Qn, we have Kc times set point of tank 3 minus the height of tank 3. So we'll have Kc times set point of tank 3 minus the height of tank 3. And then just one more, so we have Qout. So Qout is going to be just proportionality constant of tank 3 times the height of tank 3 to the 1/2 power. So going to be 3 times the height of tank 3 to the 1/2 power. Alright, so next we're going to solve IVP to solve these differential equations that we've set up. And solve IVP is just a method in Python to solve differential equations. So first we're going to call the function, and then we're going to need to give it the function that we created that has the differential equations that we want it to solve. So that's RHS is what we called it, and then it's going to want a range for the time vector, so what times do we want it to solve over. So we can say from time 0 to maybe 200 seconds, and then it's going to want it's going to want our initial heights, so we have those. So that's just the initial height of each tank. And then it's going to want to know what method we want to use, and we're just going to use method redo. There are other methods that you can use within solve IVP, but this is the one that we're going to use for this problem. And then we're going to want to set the dense output to be equal to true. Okay, so we shift in on that, and we can see it gives us quite a lot of stuff. You know, it's solved for some heights, but what we're going to want is this line right here. So this line right here is basically our solutions for these things that we can then use to plot. So we want dot solve. So it's just going to be our solutions everywhere from 0 to 200, any time that we choose between those points, and then we can put that within the variable sol. Alright, so then we're going to want to plot these. So first thing we're going to need to plot, we're going to need some times to plot over, so we can call those the times to plot, and we can have that just linear space values from 0 to 200, because that's what we did for our solve IVP, and then we can say maybe 500 points. And then, so then we're going to want to calculate our heights over these times. So we use our solve for this. So to call that, you just do solve parentheses and then t plots, because those are the times we want it over. Alright, so then we can add these to a figure, but first we need to make the figure. So fig is equal to add scatter, or so, nope, fig is equal to make subplots, and then we go fig is equal to, or fig to add scatter. And then, so our x values, we're going to want those to be t-plot. So our y values, so first we'll do tank 1, so our y value will be equal to h1. And then we can do our mode, we'll plot them as lines. And then we need to give it a name so we can differentiate between them. So the name, we can just give it tank 1. Alright. So then let's do the same thing for tank 2. And I'm just going to copy and paste these so that I don't have to type it all out again. So I'm going to have it for tank 2, and for tank 3. And then let's just shift enter and see what this plot looks like. Alright, so you can see we've got our plot here. You can see that, tank 1's blue, it starts at about 0.5. Tank 2 starts just about 1. Tank 3 starts at 2, which is what we input as our initial height, so that everything looks good. And you can see kind of how they fluctuate, and they kind of start to level out here around 200 seconds, reaching a steady state value where they will not change with respect to time. So that's what they're reaching over there, but at first they're going to fluctuate quite a bit. And this is just so this is what the heights of these tanks are with respect to time. And that's how you'd find them using Python.